Hello, welcome. I'm Chris Shankland, CTO at Odyssey Interactive. Odyssey is kind of a very small studio focused on competitive online games. I should remind you to please silence your phones if you could, and you're going to get like an email, I presume, or maybe it's in the app. I've now already forgotten about a survey. Please, be nice to me. That'd be great. And so this is how to launch an online game and still attend the launch party, and thanks for coming. So the structure of the talk here is kind of largely oriented around two case studies. Before we get to the first one, I'm going to introduce the game that the case studies are from. The game is called Omega Strikers, and I'm going to briefly discuss sort of the architecture of the game services that we used from development all the way through release. And since I put it in the title, I will point out that launch day wasn't exactly boring or peaceful, but I was first call for PagerDuty. I made it into the pictures that we took, and to the dinner afterwards. And so I think in the end, we sort of had confidence in our tech, and it seemed to work, actually. So part of the discussion about architecture, I will then define sort of observability and explain why it's necessary. The first case study is a really simple trace that's for a player's matchmaking status, which will be a bit of an orientation into what observability can look like. Then I'll dig into some of the tech underpinning kind of observability and how we implemented it in Omega Strikers. And then the second case study is a little bit more complicated, hopefully to show kind of where things can go with the observability. It revolves around kind of a matchmaking problem that we had in the actual public beta. And then finally, just some summary stuff, and hopefully there will be time for questions. So starting with the game itself, it's called Omega Strikers, like I said. Here's a short video, because it's cool. Thank you, video team. So Omega Strikers, like I said, it's Odyssey's first released game. It's a 3-on-3 competitive online game. Kind of many of the features you expect from such a game. There's matchmaking, there's in-game friends, presence, chat. We have custom games, the typical progression systems that you might have, daily, weekly missions, that kind of thing. There's Battle Pass, entitlement shop. And all the things that I just listed are what we at Odyssey call our services, or the sort of around game, which is somewhat distinguished from the core game. And I will only really be talking about the services and the infrastructure kind of to support that for this presentation. Omega Strikers launched on 8 platforms, PC, mobile, console, kind of all of them all together. We did it with a pretty small team. We were about 10 engineers. And for services in particular, we were 2 to 3 at any given time, just to give you sort of a scale of people to do what I'm explaining. And so being an online competitive game, as an engineering team, I think we have sort of the responsibility to provide not only sort of stable gameplay for our players, but really just ensure that they can log in and play whenever they want. And I think failing to meet that, especially right as the game is launching, is like a really, really negative impact on any momentum that we might be able to build. And I think just sort of personally, it feels bad if somebody can't play your game. And so in order to achieve sort of our successful launch and continue live service operation, We focused on scalability and operability as our kind of principles. So essentially, we wanted to be able to respond in minutes to some problem, while also simultaneously handling significant fluctuations in concurrent players. And so the goals there of scalability and operability kind of led us to focus on managed infrastructure, and that's very pervasive through the entire architecture of the game. And we kind of identified the general overhead and inflexibility of, we call it owning a computer, as something to be avoided as much as possible. So here is a picture of the high-level architecture of the game services in Omega Strikers. Sort of pretty briefly, game clients go and send HTTP requests to services via some kind of gateway. They receive then notifications about state changes back down over a WebSocket. The actual logic of those services run on a big bundle of Lambdas. That's like a serverless compute offering. Persistence, we're using MongoDB. They have a managed service as well. And then sort of sprinkled around in there, there's a bunch of Redis nodes that do caching for us, also on a kind of managed offering. There are game servers, as it turns out, and we, as may not surprise you, use a managed service to handle scaling them up and down, and as well as place matches. There is a computer that we might describe as owned in the middle. That's the match finder. It's a single box. And it just sits there and kind of spins over an in-memory list of players and then spits out matches when they're found. And then all of these pieces of infrastructure talk to our observability service, which I'll talk about a bit later. And so the key thing I think about this is that, as I've said repeatedly, they're all managed services, which gives us the ability to scale quite nicely. And as a result, the computer doing the actual work may actually be ephemeral. It may go away, or we may not have control over it. And so if we want to do a typical thing, like log into the box and see what happened, you may not be able to do that because either it's gone, or you just aren't allowed to, or whatever. So that's kind of a big blind spot, and it makes it really difficult to operate these kinds of services. And that's what observability really, that's the hole that it's plugging. And just before we move on, I'll sort of highlight two notable decisions, well, I think they're notable anyways, about how we actually made use of this. And I would describe them as probably opposite sides of the conventional best practices spectrum. The first one, which is the probably good side, everything was automated in terms of deployment. We aimed for one button. We ended up with 3 buttons, but it's not that many. And that was sort of a core safety blanket for us in terms of really responding to really, really high demand, or if we had a really significant outage, we sort of had this in the back pocket where we could spin up the entire stack in another zone, region, wherever, or potentially concurrently in multiple zones if we really had big scaling problems. And there's a requirement to really maintain that ability. Usually it'll be every couple of months or weeks you spend a few days yelling at computers because it's not working, but it was totally worth it. An example of the value, we had a play test that we heard about only a few hours before it was supposed to happen in Asia, and we were able to just click the buttons and it worked, and I was like, great. And so it didn't disrupt any of our daily play tests or any other really development process. So we'll move on to the unusual choice. For Omega Strikers, it's there's a single environment, just one. It handles live game. It handles internal playtests. It handles literally everything. So when you make an update, it's going live now, and that means that development features, upcoming content, absolutely everything is always in production. So this forces us to implement sort of logical barriers to enable testing or protected actions. But the upside is that there's only one process, and we do it every day or potentially multiple days. And so we're really used to it. And as I will talk about later, that's really, really helpful. So changes get put out quite frequently, and there is a risk to that, but you can kind of mitigate that, or we mitigate that through pretty extensive automated testing, in the sense of like end-to-end testing, and then there's feature flags, and actually rolling out a change is quite quick. So if it goes out and it's bad, you just undo it. It's like not the end of the world. And I think, again, the big upside of this single environment is that in the scripted deployments, is that for each individual change is actually relatively low risk. And like I said, you can kind of just undo it, and it's very incremental in that way. And the other big thing is you're never migrating or you're trying to do like any integration between these environments. It's always there. So like I alluded to, a major downside to the managed infrastructure, and especially these kind of ephemeral compute offerings, is the significant increase in difficulty of debugging the thing when it's actually running. There's several factors, I think, that contribute to that, but generally it's just like hard to isolate a particular change or figure out what the heck it was doing at that time, or reproduce it in any sort of really controlled fashion. So solving that is obviously something that we are going to need to do so that we can actually use these things at scale. And so I'm going to define observability kind of informally, and it's really the ability to inspect or sort of otherwise know what the state of an application is while it's doing processing. And logging is an example of a common, but I will classify it as somewhat rudimentary form of observability. In Omega Strikers, what we use is essentially a highly structured logging, systematic instrumentation, and then a queryable UI all together to solve these problems for ourselves. And we'll dig into the really sort of more specifically how that looks, again, a little bit later. But for now, I just want to highlight a couple of things that this allows us to do, which are really significant time savers in debugging, and I think as a result really increase our reliability. The system is always on. It's always recording. There's it's like a 30-day buffer, but it potentially could have been longer or shorter. But it allows us to kind of go back and investigate problems after they've happened. So we do daily play tests, and this was like our primary testing of the game, more or less. And so someone would say, hey, this was weird, or this was busted, or whatever it was, and like we were playing the game, so we were not like monitoring this stuff. But we were able to go back in time and look at the state that they had at that time. It was all captured, and just trace through and be like, yes, that's right, it was busted here, or no, you're wrong, that's actually how it's supposed to work. And it's a proactive as well. It's sort of real time. So when you release new code, you can just like look at if it's doing what you expect. So you can fully inspect the system. Okay, so we'll start with the first example. It hopefully kind of illustrates now what I've been describing for the last few minutes. This is like a sample of the UI that you would see. And it's a really simple matchmaking status query. The focus here is not on this particular request, but sort of on how this data is structured and presented, that hopefully will illustrate some of the benefits. Each row, so some nomenclature here, each row is called a span. Spans are typically organized in sort of a tree-like hierarchy. The one at the top is called the root. And the collection of related spans is called a trace. And typically that's going to represent some logical operation. It's kind of context dependent. Every span usually has some common data, like it'll have a name, a duration, and then it'll point at who its parent is. And this allows us to create this kind of waterfall type visualization. And just with that, we're able to see how long individual functions take basically within these requests. We can aggregate them across multiple requests or by players. And this is essentially what we use to do load testing and profiling. So by itself, I think that's pretty valuable. But then there's a bit more. So each span, you can give it kind of this custom bag of data. So here's an example of a few things that are useful. And then those get indexed basically, so you can query on them and look for related spans or traces. So here's like, I don't actually remember what I highlighted there, but the game version, for example, would be useful things to query against. So here's a different trace just to sort of highlight the value of the built-in timing. It should not take 30 seconds to log into the game. And we pull this up, and we know exactly what step actually took all of that time immediately. It's kind of like a profiler, but it's always on. And finding this takes like 10 seconds. You're like, hey, find me things that took a long time. Oh, this is bad. OK, so we'll move on now to sort of what an implementation might look like and what tools are out there to use for your own code. At its core, right, this data is kind of just semi-structured JSON. Like that's what's being passed around. Fortunately, there's sort of a standardization body. It's called OpenTelemetry. They identify a few common property names that are expected to exist. So these are like, that's the name and the parent and the timing and those things. They have like almost like a schema. And outside of those, the rest of the data is pretty context sensitive or context dependent. You kind of give it whatever you want. So we ended up building a pretty small set of utility functions that made it really easy to integrate like spans and traces into the services code. And we, through fairly continuous effort, we ended up with like about 1,200 instrumentation points last time I checked. The number goes up like every time you write a function. We just always wrap it in a trace or a span. There are lots of frameworks that you could use that have like sort of built-in instrumentation for this kind of thing. So it's not like there's this massive labor cost. We didn't actually use anything like that, so we did it ourselves. And then we're able to use that integration then to facilitate sort of debugging across all phases of production. So development stacks, your unit tests are running this code, so you can actually look at them. And then having them all visualized in this single tool is really nice. It's like, again, back to the sort of, you're used to this process from all points of development. And then to actually aggregate things and visualize them, we use a vendor to store and index this data. There are lots of backends. You can kind of just Google them, pick your favorite one. Here's like a kind of cool picture that OpenTelemetry made, which is great, to sort of show what the internals of the observability system itself are doing. You got your various producers, and they're sending data to these service or services that are called collectors. The collector then is doing something, probably indexing, maybe a database is involved, and then it's feeding some kind of front end to assemble however the visualization is. Could be the waterfall, could be something else. And then typically it'll provide some kind of querying interface as well. So you can look at interesting things. I'll just point you kind of to the OpenTelemetry documentation for any really specifics or to go deeper on that. So now we'll move on to the second example. It's a little bit more complicated. But the idea here is to show that you can look at data from multiple systems together to solve problems that I think would be pretty challenging without some kind of centralized system. This is sort of a recreation because the data is aged out, but a recreation of a real problem that we had in our first fairly large public test. We were sitting there playing the game. It was great, and then all of a sudden, people were not matching for relatively short periods of time. It was like 15 seconds-ish. It's kind of, when you get like a DM from Discord, it's kind of hard to know exactly what they're doing. And then some groups like weren't matching at all. Yeah. And so the first thing to do, this is a matchmaking problem, right? So we go look at the matchmaker, and it's like, okay, this is bad, but what is going on here? So we can basically zoom into the last trace before one of the dips, and again, the useful part of that is this may or may not be actually happening live, but I don't care because I can go back and find a case of it that it was happening in the past. And so you kind of drill down into this particular match finder trace, get that last one, that's great. and we can look at some of the context data we've got here, which in our case, we were specifying, these are the actual groups that are in the queue. This actually looks fine, so this is probably not the problem, but maybe this one at the front is suspicious. So let's go ahead and dig further into that. So query, hey, give me things that are related to this group. I've sort of filtered out all of them, but you would see like the construction of the group, so you can see the invites for them and who accepted and how that was actually done. But the relevant one for us is like, okay, well, they're getting added to the matchmaking queue, so who was in their group, what happened when that addition happened, maybe that data is what's suspicious. And it turns out, unsurprisingly, because it's kind of a guided tour, that this is the one that's wrong. They're all forwards, which probably doesn't mean anything to you, but in our game, you have to have a goalie, or at least that's what the match finder decided. And so it was sitting there trying to construct groups where one of the teams was full of forwards, and it was like, I don't know how to do that. And so then they would sit there and plug the queue for essentially the timeout for them. So they would fail, and then people would go through, be a big burst, and that was the chart. Okay, great. So now we know the problem. We basically then hacked in a really quick fix so that, okay, we just ignore what you wanted to be for now so that people can play the game. Throw a test case in, actually fix it properly in the matchmaker, update the matchmaker, and then we're good again. And the total time kind of to do this was in the 25-minute range, which I think is pretty good, because we're aggregating data across multiple things. There's hundreds or thousands of matches being made per second at this time. Not the picture that I showed you, but I promise it was like that. And so being able to drill down into that data really quickly is solving a big problem. But it's not quite as valuable when you aren't able to also operate on it. So that's kind of our principles in action. So kind of in summary, we kind of kept our infrastructure as simple as possible while still addressing the problems that we were trying to solve. We use the same process every day, from early development all the way through to launch and into live service as well. So we were really familiar with it. And so when there was a problem, we weren't trying to remember oh, how do you do whatever in production, or how do you do it in stage, or what's happening. No, there's just the one thing. I think the investment commitment to observability really meant that we could understand what was happening, so we could drill in directly, quickly. There was, again, a single tool. You just go here and find it. And then lastly, on launch day itself, we really significantly over-provisioned the infrastructure, just give ourselves a buffer. This flexibility is exactly what the managed services were supposed to provide, and they did it, and that was great. And yeah, it cost more than it maybe should have, but the thing ran, and then you can scale it down very quickly over the next couple of days or weeks once you identify what your players are doing and how many of them there are and what you need to do there. So I kind of think of that as a marketing expense, realistically. If you're trying to sell that to someone, get some marketing money to run your servers. Okay, that's it. Thanks for coming. I can take any questions. You asked that you go up to the microphone if you have a question.
Hello.
Hi.
Talk. I was curious about your match finders. You said, is it literally one machine?
Yes, it's a single C5 large. It's like a little baby machine running, and it can produce 3 million matches per second.
Wow, okay. How do you patch it if it's one machine without taking prod down? Or do you just take prod down for a brief downtime?
Oh, we just spin up a new one. So there's queues and Redis around it.
Right.
So you just kind of pop one up, and that one takes over, and you drop down the other one.
Interesting, yeah. So for my matchmaker, I recently decided, against external advice, to do in-memory as well. And I was like, well, it's probably fine. So
it's pretty fast.
Yeah. It's like I think we as a distributed systems sort of tech space shied away from any kind of in-memory anything when we figured all this stuff out. But I think if you're calculated about it, you still can do in-memory sometimes. So it's validating to see somebody else do the same. Thanks.
Welcome. Thanks.
Alejandro, producer, but ex-Apple software engineer for 7 years, did SRE, live ops, DevOps kind of stuff. Very interested to see your basically like mono repo style, like single branch production, because that was not my experience, but curious to see if you think for a game like Omega Strikers and maybe other games where maybe you aren't developing too many features that would be maybe taking months to develop and then needing special integration. Do you recommend that maybe other games maybe take this similar approach using feature flags and end testing and using that just for simplicity's sake, especially for the simplicity of automated 1 to maybe 3 button launch? I
would, yeah. I mean, I think it was great. And we have features that took months to develop. You just build them in the branch, like turn off the code, don't call the code. Obviously there's like 2 or 3 of us, so it's a lot easier for us to communicate with like, hey, don't call these functions, please. They're not ready. I think there are probably process ways to address that at a larger scale. I had another thing that is just gone.
I'll just steal in that time that you just lost in that thought. Testing. You do unit, functional, and then end-to-end, or just do you focus on like the last functional? We
pretty much just ran full end-to-end, spin up the whole stack locally. We use some Docker for that, and just run the whole thing. Because I don't know, that's what's actually running, and so especially we have to be able to observe those things anyways. So that's just part of the stack, and then we know it's going to work because we tested literally the whole thing.
Cool. Thank you.
Thank you.
Hey.
Hi.
I'm also a big fan of OpenTelemetry. One of the issues I've seen teams try to solve is volume of events. So you showed a trace that had every function call generating span and being sent to the vendor.
Yeah.
I wonder, have you had to deal with volume problems and costs? And
so I have a slide that I removed, but yeah, it was massive when we launched. We were sending like almost 1 trillion events a day. You do some sampling, basically, is how it boils down. It's a really challenging problem, I think, to solve. Where we are now is there's baseline flat sampling, like at the actual event creation, because otherwise you have to centralize the whole volume of data, and trying to do any analysis on it becomes really challenging because the volume is so high. But then we have special paths through, so like any cert requests, for example, they're never sampled. We want to know what's happening in cert, or we want to know what's happening in dev. We're able to turn traces on for individual players. And these are sort of just like overrides that we've learned are very useful for us. I think it probably depends on what your particular context is and what is useful information. But yes, that is a hard problem.
Okay, cool. That's good to know. Is it basically like you could turn it on the root span? Like, okay, the root span and all child spans are going to get sent.
Yeah, so we keep most of our root spans because we like to see kind of how many requests are happening, but we throw away the rest of it, essentially. And so it basically just rolls a die at the beginning of the span and says, we don't need you. If there is then a fatal error or something, it'll keep the stack, basically, because that's kept kind of in memory. Ideally, we would buffer all the requests, probably, the whole trace, while the request was happening, so that if we do hit these error cases, we can like dump the whole thing. Right. But it's been pretty useful just to be able to see that particular stack, basically.
Cool. Hey, thanks.
Yeah.
Hello. I don't know if this is okay to ask, but with the sad news of Omega Strikers, I want to ask: is there still a team that looks into the problems and all these, for example, errors or bugs, or anything else? Is there like a small team, or is it like when it pops up, it's like, oh, can someone like check that out or like deal with that, or how does that work in?
Yeah, we still have people full time on Omega Strikers.
Okay. Got it. Thank you.
Thanks.
Cool.
Probably last one, but yeah, okay, great.
Yeah. So running a live game as well, and I think one of the interesting things you brought up is that your server backend is entirely all prod, all forever. But that also means that you have a high potential of leaks and stuff. Like when that also means you also have like code duplication, right? So if you have something that's not backwards compatible, for example, you're going to have old code and the new code. How do you like maintain that and make it so that people aren't duplicating all their work over and over again when they're back compating?
Yeah, so I think there are a couple of questions there. The first one is like worrying about leaks. We worry about them, but not like too much.
Okay.
Like it's probably stuff we're going to release anyways. If it leaks, it's not like maybe the end of the world. Obviously, we try to avoid the leaks, but it's not going to end the game.
Gotcha.
And then the backwards compatibility thing, we basically duplicate APIs if they're going to change significantly. You just go for V2, and great. And then you, in theory, delete it later. I don't know if we've ever done that, but we probably should.
Right. Okay. So it's normal code duplication is fine. Just deal
Yeah.
with it later.
Copy and paste is there for a reason.
Okay. Cool. Thanks. Oh, jeez.
All right, thank you.